Okay, so we're going to begin looking at kind of a very simple example. In fact, this is going to be very similar to the example that we did 2 videos ago, just with going through explicitly the steps that I went through, and I'm going to give you an explicit curve, not just an f of x, or sorry, an explicit function. All right, so I'm going to start with the t derivative of u plus 2 times the x derivative of u is equal to 0. And then we know that u is equal to x squared on the x-axis. Okay, and I'm going to follow this format basically for all of the problems. I'm going to write the problem here, meaning the PDE and the initial condition. And then down below, I'm going to give a parameterization for the curve. So the curve is the x-axis. Okay, now if I wanted to be like, if I wanted to match things up exactly how I had it in the previous very generic video, I would say the parameterization is going to be something like theta 0 for theta being a real number. There's nothing wrong with that, but I think it's a little more expressive to say x naught 0. So we're going to look at x naught 0 for theta being, and now for x naught. Okay, and if it was the t-axis, which we'll see examples, I would have 0 comma t naught instead of x naught comma 0. So we're thinking about x naught as being, it's fixed, but it's a generic fixed point. We're gonna have a system of equations for every single x naught. Okay, and then our system of equations, we're always going to have this. So I'm going to use this format here. I'm going to have x prime of s. It's always going to be equal to the thing multiplying the x derivative. We're going to have t prime of s. It's always going to be the thing multiplying the u derivative or the t derivative of u. And then z prime of s, once we move all of the derivative stuff on one side, it's going to be whatever is going to be on the right-hand side. And then we're going to have x of 0 is going to be whatever the corresponding value is there. T of 0, whatever the corresponding value is there. And then z of 0, we just, to the solution we just plug in, is going to be whatever u is on the solution, or on the curve. Okay, and all the black stuff I'm going to keep here. I'm just going to keep this up for every single problem and just erase all of the other stuff. So x prime of s, it's whatever is multiplying the x derivative of u, that's 2. T prime, it's whatever is multiplying the t derivative of u, that's 1. Z prime of s, it's the right-hand side, that's 0. X of 0 is going to be equal to x naught. T of 0 is 0. And z of 0 is just going to be whatever, you take your initial condition and plug it into there, which is going to be, in this case, x naught squared. T is equal to 0. Okay, and so we're going to have this for every single problem. We're going to start with this. All right, now the next thing that we're going to do is we're going to solve this system of differential equations. Now, in terms of systems of differential equations, you can't really ask for anything easier than this. The solution to x prime of s equals 2. We're going to have x of s equals 2s plus x naught. We're going to have t of s is equal to just s plus 0, and z of s, well, z prime equals 0, so z is constant, so it's just going to be equal to x naught squared. So it's just going to be equal to x naught squared. All right, now what I like to do, just to get a visual of what's happening here, I want to sketch some of the characteristics, and I'll probably try as best as I can. Well, I'll probably have to redraw these coordinate axes each time because the curve here will be a little bit different. Notice it's also extending out at the negative x-axis and all down, well, negative t-axis, positive, negative t-axis, negative x-axis. Then I'm just going to draw it like this for now. And so what we're doing is if I start at a generic point here, x naught, these curves, by the way, are called characteristic curves. The curves defined by x and t are called characteristic curves. And in this case, if I have x horizontal, t vertical, which I will always have, this is going to give a slope of 1/2. So I'm going to go over 2 and up 1. So over 2, up 1. I mean, it doesn't have to be exact. These are the exact same things we had before. If I pick another x naught, let's say here, it's again going to be going this way. These are parallel, but they also extend back this way as well. If we're thinking about t as being a time variable, that would kind of be, correspond to going back in time, I guess. Okay, so now what this says, if I pick any point in the xt plane, let's pick a generic point like this. In the xt plane, if I want to know u at that point, what I need to do is, I know that on these characteristics, I know that my solution is going to be constant. So on this purple characteristic here, u is equal to x naught squared. So for any point on this plane, u is equal to x naught squared. Or sorry, on that line, u is equal to x naught squared. And similarly, for any point on this line, u is equal to the blue x naught squared. Okay, now what happens if I look at this generic point? I mean, when we solve a PDE, we don't, start with here and then, say, okay, well, on this line, this is what it is. On this line, this is what it is. When we want a solution to a PDE, we want to go the other way around. We want to start with a point in the plane and then figure out what the solution is. So in this problem, it's very simple. We just need to sort of trace this back to the boundary, back to the curve gamma, figure out what that x naught is, and then on this line here, u of xt is just going to be equal to x naught squared. So given a generic point here in the xt plane, I trace it back to x naught. In general, this will depend on both s and x naught, but here it only depends on x naught. I just need to figure out, given xt, what that x naught is. Well, I do that by solving the following system of equations. I know it lies on this curve for some x naught. So I need to solve the equation x, or the system of equations, x equals 2s plus x naught, and t is equal to s. So in general, I'll need to solve this for both s and x naught, because like I said, this can involve both s and x naught. Well, when you solve this, you get pretty clearly that x naught is equal to x minus 2t. And so what this tells us then is u of xt for this particular point x comma t, but it's generic, u of xt is going to be equal to x naught squared. That's what this says. But for this xt, the corresponding x naught is x minus 2t. So this is equal to x minus 2t squared. Okay, I just want to mention a couple of things. I want you to show that this function satisfies both the differential equation and the initial value. I want you to verify that it solves it for all values of x and t. So what we have here is called a global solution. It works no matter what value of x and t you put here, you're going to get a function that satisfies both the differential equation, and then for t equals 0, it's going to satisfy the boundary here. This is something called a global solution. We're going to go on and see, even for linear equations, not all PDEs are going to have global solutions. There's different things that we have to do, but this has a global solution. Okay, that last part about global solution, that's just a little extra. If you are confused by that, just forget about it for now. Think about the methods that we're using here to solve this differential equation.